Start off by looking at this problem. This is a collision which involves an oblique central impact, and what you're seeing right here is the line of impact, and keep in mind that that will also designate the normal, and so let's just put an arrow on that and label that E normal. And then of course over here we'll have E tangential, which is always perpendicular to the normal. So there's a 90-degree angle in there. And then these two spheres collide at that point, and we see that there's a 40-degree angle between the velocity of sphere B, and sphere A is over here, and it's got a vertically downward pointing velocity. You'll notice in the problem statement I use the word speed here and here. That's the magnitude of the velocity and not the velocity vector itself. But the vector values are going to be very important. Now VB is the easy one, because it has a velocity designated along the line of impact. So V sub B as a velocity is equal to the magnitude of V sub B, which turns out to be 2 meters per second right here, times the normal unit vector. But V sub A is going to take a little work. Now I want to make sure I get this down straight. So here's the direction of V sub A, straight down. Keep in mind the tangential coordinate is in this direction, and the normal is off in that direction. I'm drawing this large so I get a real good sense of where things are. This angle in here, by vertical angles, these two angles are the same, so that means this is my 40-degree angle. So as I look at V sub A, I can break it down into a component along the tangential direction. That component is going to be V sub A magnitude. Here's 40 degrees. This side is opposite the 40-degree angle. So sine 40 degrees. And that is pointing in this direction, down and to the left, which is opposite of E tangential. So minus sine E tangential. And then there's a component in this direction, and that's pointing opposite of E normal. This is adjacent to the 40-degree angle. This would be minus because it's in the wrong direction. E normal points this way and the velocity is pointing that way. V sub A cosine, because it's the adjacent side, 40 degrees times E normal. So again, as I look at the components of V sub A, there's a component in the tangential direction. So this would be V sub A tangential. That's right here. And there's a component in the normal direction. That would be V sub A normal, and that's right here, including the minus sign. Here's the velocity of A as a vector. If I have this collision, keep in mind, tangential component of each mass will remain the same before and after the collision. Of course, VB has no tangential component, so not a problem. Here's the tangential component of V sub A, so that's going to remain the same. Speed, remember, is 2.5 meters per second. But in the normal direction, momentum is conserved, and we have the coefficient of restitution. So looking at conservation of momentum, anytime I have a collision, I'd rather think conservation of momentum. So it's the mass of A, velocity of A in the normal, plus the mass of B, velocity of B in the normal. Well, that's going to equal the mass of A, which is 1.1 kilograms, times the velocity of A in the normal, which is right here. And that's going to be negative 2.5 meters per second cosine 40 degrees. Plus the mass of B, 0.7 kilograms, times the velocity of B in the normal, but B is all in the normal, so that's 2.0 meters per second. So there's the normal component of the momentum before the collision takes place. When I work that out, I get negative 0.7066 kilograms meters per second. Now this is going to equal 1.1 kilograms. That's the mass of A, times the velocity of A in the normal, plus 0.7 kilograms times the velocity of B in the normal. So you'll notice I have two unknowns in this equation. So I need another equation. Well, that other equation is going to be the coefficient of restitution. The coefficient of restitution says E equals U B in the normal minus U A in the normal, don't know either of those, divided by V A in the normal minus V B in the normal. Always the normal component, but I know both of these. And I know the coefficient of restitution. So 0.75, I'm going to bring this term over this side. I multiply by V sub A normal, which is right here again. So that's 2.5 meters per second, cosine 40 degrees, and that's negative. So minus 2.5 meters per second, cosine 40 degrees. Sine is very important. Minus V sub B in the normal, which is all the 2.0 meters per second, because that's all in the normal direction in this particular problem. 2.0 meters per second. And that's going to equal 2.936 meters per second. That's negative. And that will equal UB normal minus UA normal. So that's a second equation into unknowns. So to rewrite, I've got minus U sub A normal plus U sub B normal equals minus 2.936 meters per second. And then going back to this equation, I'm going to divide everybody by 0.7 kilograms. So this term right here, when I divide by 0.7 kilograms, is going to be minus 1.00946, minus 1.00946 meters per second, because the kilograms will divide out. I want that on the other side. So minus 1.00946 meters per second. Coefficient of U sub A would be 1.1 over 0.7, which is 1.57, U sub A normal, plus U sub B normal. Keep in mind when I divide by 0.7 kilograms, that becomes a 1. And let's change the sign on everybody in this second line. That's negative, that's positive. So what I'm going to do to solve is I'm going to add these two equations together. See, the UBNs will cancel out. One's positive and one's negative. I get minus 2.57 U sub A normal equals, I have the 2.93 and the 1.00946, and that gives me a minus 1.92687 meters per second. So I'm going to divide by the 2.57, and I get U sub A normal equals 0.749756 meters per second. Substitute that into there, and I will get U sub B normal equals minus 2.186 meters per second. And so the velocity of A will equal, there's the velocity of A in the tangential, and that won't change. That's 2.5 sine 40 degrees, which is 1.607 meters per second. That's in the tangential direction, plus 0.749756 meters per second in the normal direction. U sub B is equal to minus 2.186 meters per second in the normal direction. So converting that over, here's E tangential and E normal. Let's do B first because it's the easy one. So minus 2.186 meters per second E normal says that it's going in that direction. 2.186 meters per second. This would be a 40-degree angle, and so I'm going to have a component in the negative y, component in the positive x. So in the positive x, that's 2.186 meters per second times the sine of 40 degrees, and then the negative y, it's 2.186 meters per second cosine 40 degrees, and that's in the negative y. The velocity of B would be 1.405 meters per second in the I, minus 1.675 meters per second in the J. There's the velocity of B. Now the velocity of A has a 1.607 meters per second in the tangential. And this would be 40 degrees. The velocity of A equals 1.607 cosine of 40 degrees in the I direction. That's meters per second, plus 1.607 meters per second sine of 40 degrees in the J direction. Now that's just the tangential component. And there's 0.750 in the normal direction. This is going to be 50 degrees. This is 90. And the whole thing adds up to 180. So I've got 40 here, plus 90 is 130, leaves me 50 degrees for that. So plus, and actually minus, because it's pointing left, minus 0.750 meters per second, cosine 50 degrees. And then it's up, plus 0.750 meters per second, sine 50 degrees. J hat, this is I hat here. And so I get 0.749 meters per second in the I hat direction, plus 1.61 meters per second in the J hat direction. And that's the velocity of A after the impact. Alright, here's another problem. We've got a spring between the wall and a 10 kilogram block. There's a 500 Newton force. You can see it's at an angle, making a 3-4-5 triangle. And I want to know the velocity when s equals 5 meters. Now, since I'm looking for velocity and I'm given position, this position is the important one. Since I'm given position and a force, I'm pretty sure this is work and energy. So I'm going to use a combination of conservation of energy and work. I'm going to start off with some kinetic energy T1 and some potential energy, which is due to the spring. I'm going to call that spring 1. And then the work done by the force of 500 newtons, which I'll call the work done by F. According to work and energy, this is going to equal the kinetic energy later plus spring potential energy later. So I add all these together. So an energy bar graph might look something like this. I have no initial kinetic energy, no initial spring potential energy because it starts from rest and the spring is uncompressed. Starts from rest means kinetic energy 0. Spring is uncompressed means the spring potential energy is 0. Then I also have the work done by a force, U sub F. We'll just give that 3 bars of energy. Then later on, there's going to be some kinetic energy, T2, and some spring potential energy, V sub S2. And we'll give the kinetic energy 2 bars and the spring potential energy 1 bar. Don't really know if that's accurate, but there you go. So I want to know the velocity when I travel to half a meter. So the work done is the integral of F dx, but the force is constant, so it's just F delta x. And I'm only interested in this component of the force. So 500 newtons times the cosine of theta, which is 4 over 5. That's going to make that force 400 newtons. Now that force has a component to the right, and my displacement is to the right. So right-hand force, right-hand displacement, positive work. I travel for a distance of half a meter, so there is work done by the force. I can add in kinetic and potential energy, which are 0. Now that's going to equal the kinetic energy, which is 1/2 m times velocity squared, don't know what velocity is, plus 1/2 k, which is 500 newtons per meter, times the distance, which is half a meter, and I square that. So the left side, I get 200 meters equals 1/2 10 kilograms, velocity squared, plus 1/2 500 newtons per meter, 0.5 meters squared. I have a 1/2 in both terms, so let's multiply both sides of the equation by 2. That'll give me 4,000 newton meters on the left side, 10 kilograms times v squared on the right, plus 500 newton meters times a half a meter squared, and that's 125 joules, which is the same as a newton meter. I can bring that to the other side of the 4,000, and I get 3,875 joules equals 1/2 10 kilograms times v squared. And so v is equal to 27.8 meters per second.